Everyone talks about quantum computing like it's magic, but let's get real. What actually makes a quantum computer tick? Start with qubits, the heart of it all. Qubits are like bits, but different. They don't just hold a 0 or 1, they can exist in both states at once. That's superposition. And when two qubits interact across space and time, that's entanglement. But how are they made? Qubits can be created in different physical forms, superconducting circuits, cooled near absolute zero to eliminate resistance, trapped ions, atoms suspended in electromagnetic fields, photonic qubits, light particles manipulated with mirrors and waveguides, topological qubits, theoretical, but designed for extreme stability. Now compare that to classical computers. Classical CPU executes instructions. Classical RAM stores temporary memory. Hard drive stores data long-term. But quantum computing rewrites all of that. Quantum processor, the quantum CPU, a highly isolated chip that manipulates qubits via quantum gates, quantum memory, not yet standardized, but involves systems to coherently store and retrieve entangled states. Quantum hard drive? Not exactly. Data can't just be stored statically. Measurement collapses the state. Quantum storage is still evolving, often hybrid with classical backups. Now let's talk software. You can't run Windows on a quantum computer. You need a quantum operating system, and it's being built now. Projects like Qiskit, IBM, Cirque, Google, and PennyLane, Xanadu, are building quantum software stacks that let developers write algorithms in high-level code, which then gets translated into quantum instructions or circuits. Quantum software isn't about apps. It's about writing logic that manipulates probabilities. You build it using quantum gates, like Hadamard, PolyX, and CNOT, hybrid classical quantum systems, where a classical computer controls the quantum logic error correction layers because qubits are fragile. Quantum software is probabilistic, nonlinear, and entirely alien to what we use today. You've seen the hardware, you've heard the buzz. But what really makes quantum computers powerful is the math beneath the surface. Quantum algorithms. Unlike classical algorithms, which follow a straight line of logic, quantum algorithms use superposition, interference, and entanglement to solve problems faster, smarter, and on another level entirely. Let's break down the legends. Shor's algorithm. This one changed everything. It can factor massive prime numbers exponentially faster than any classical computer. Why does that matter? Because most of today's encryption, banking, emails, blockchain, is built on the assumption that factoring is hard. Shor's algorithm makes it easy. And that means quantum computers can break modern cryptography. Grover's algorithm. Think of this as a search cheat code. Classical search, ON. Grover, ON. That's a square root speedup across massive databases, AI models, or decision trees. It's not just faster, it's a strategic weapon for optimization, recommendation, and intelligence. Quantum Fourier transform, QFT. The backbone of many quantum algorithms. It takes frequency data from chaos to clarity, unlocking pattern recognition that no classical system can achieve at scale. And there are more coming: quantum machine learning, quantum simulation, quantum chemistry algorithms that can model atoms and molecules with atomic precision. These aren't just upgrades, they're weapons of computation. But here's the catch. Without funding, without education, without bold leadership, these algorithms stay trapped in theory. This message is fully supported and co-signed by Kevin Brown, because understanding the algorithms of tomorrow means one thing: you can control what the future solves and who it serves. Understanding this isn't about curiosity, it's about preparing for the future of intelligence, engineering, and power.